Hi viewers, welcome back to another video. In this video, we are going to see a very important topic. See, we have been seeing this kind of pulley mass systems for years and years. And along with those kind of questions, there will be certain assumptions. Have you really understood what each of those assumptions mean? And what are the implications of provoking each of those assumptions in doing a particular problem? Or how each of those assumptions make our life a little bit easier to solve the problem? In this particular problem or in this particular video, we will look into all these assumptions listed over here. What do we really mean by a frictionless pulley and what are its implications? Then when it comes to massless pulley, what are the implications? Then you would have heard about inextensible string or inextensible cord. What is the physical implication of that? Then at some point of time you would have heard that there is no slip between pulley and rope. What does that mean? We will look into each of these things one by one. We will start off the discussion by describing the implications of the assumption massless rope. So we will consider a system like this. You have a pulley and you have a rope or a string that is going over the pulley, and there are two masses, discrete masses connected to the rope M1 and M2. For the time being, let's assume that M2 is greater than M1. That means with some acceleration A, let's say with some acceleration A, this whole system will try to come down. Okay, then M1 will also come down. So that's how the system is behaving. In the first case, now what I'm interested in this portion alone. Okay, I'm interested in this portion of the system, and I'm drawing two cases. The first case, my assumption is that I have a massless rope, and in the second case, I'm considering that my rope is no longer massless, it is having a density of rho and it is having a cross-sectional area capital A. So what I have done here is I have taken a free body diagram of the mass plus x length of the rope. That's why I have shown x over here, and I have written T of x, tension acting at a point whose distance is little x from the mass M2. The same applies here. So I've taken the free body diagram and I've marked the different forces acting on the system. So let's call this case 1 and call this as case 2. So for case 1, if you write down, things are far more easy. Let's say for the case 1, if I write down Newton's second law, then I will end up like this. M2 times the acceleration will be equal to M2g, because I'm taking the positive direction of A downwards. Okay, positive direction of A is acting downwards, minus T of x. From this, I can write T of x as M2 g minus A. Make sense? If you look at this expression very carefully, even though I wrote it as a function of x, if we look at the right hand side carefully, then we will be able to appreciate that T of x is no longer a function of x, which implies that tension in the string is uniform for a massless rope. Now do the same kind of exercise for this particular case, where the mass is having some kind of where the rope is having some kind of mass. Now invoking Newton's second law, here M2 plus the mass which is coming from the rope times the acceleration is equal to m2g, which is acting downwards, minus t of x, then again the mass of the rope, which will be, sorry, I made a mistake there, rho x a g. From this expression, if we write down an expression for x, then we will end up here, m2 plus rho a x g plus minus m2 plus rho a x a. This expression clearly tells you that tension along the string is no longer uniform. It is varying as a function of x. So if you want to assume that the tension is uniform throughout the string, at least till it reaches, you can say at least till it reaches this particular point over here, until it reaches the next disturbance, or until it reaches the next mass in a Pulley mass system, if you want to assume that the tension is uniform along the thread or the string, then it should be a massless rope or a massless thread. Make sense? So I hope next time when you hear the word that massless rope, the thing that should strike your mind is that now I can go ahead and assume that the tension in the string is uniform. Let's move to the next assumption, frictionless pulley. Again, an important assumption that we will come across multiple number of times. So let's say I have the same system drawn over here. There is no friction between the rope and the pulley, and then there is no friction between at the hinge point of the pulley as well. It is interesting to note that when you have no friction, then even for a scenario where m2 is greater than m1, that means when you have your m2 greater than m1, this whole system, this rope plus these two masses will come down this way. If you have a frictionless system, then the pulley won't move at all. Clear? So in this kind of problems, when you have the assumption of frictionless pulley, then you don't have to worry about the motion or the dynamics or the kinematics of the pulley. You can leave the pulley alone. The pulley won't even move when there is no friction. Here I have drawn the free body diagram of both the string as well as the pulley. If you examine the diagram very carefully, here you can see these two tensions are coming from the masses, and then there is a reaction force that is applied by the pulley on the rope as shown over here. Similarly, every action has an equal and opposite reaction, Newton's third law. Now when we come to the free body diagram of the pulley, then we have something like this, where you have radial forces, which are the force applied by the rope on the pulley. See, since all these forces are acting radially, there won't be any tangential force on the pulley to make it move. See, to make something or to make this pulley rotate, there should be a tangential force, because this particular tangential force will cause a moment about this point, and that will set the whole pulley into motion. But in this scenario, there is no tangential force. There is no tangential force at any of these points. Had there been friction, then there would be some tangential force acting at these points, which will cause the pulley to move. Make sense? So next time when you hear the word frictionless pulley, you need to appreciate the fact that the pulley won't be in motion. The pulley won't know what happens over it because there is no friction, there is no tangential force. Make sense? one small thing, one tiny little thing that I need to add. Whenever you encounter a problem in kinematics or dynamics, the first thing you should try to draw yourself is the free body diagram and identify the action reaction pairs. That will do a world of good to you, and it will give you, or it will help you a lot in getting some intuitions into the problem. One more information before I wind this up and move to the next point. See, when you have friction between the interfaces, then there is a particular expression that connects the tension between the tight side and the slack side, which is given here like this: T2 by T1 equal to E raised mu theta, where mu is the coefficient of friction and theta is the angle in radians. If you want me to draw that theta here, for this kind of an arrangement, this will be the theta. So remember that there is an expression that connects the tight side tension and the slack side tension, especially in a belt drive and all. You will see this kind of expressions. So I just wanted to tell you that there are formulas like this when there is friction present between the pulley and the rope, and when friction is present, this will make the pulley to rotate. So you have three things in motion. You have your M1, which is moving down, which you see, when you have friction, you have M2 moving downwards, M1 going upwards, and then your pulley rotating. When there is no friction, or when you assume that the pulley is frictionless, then you have your M2 coming downwards, M1 going upwards, and your pulley is just at rest. Okay, now let's move to the next. Inextensible string. See, you say in most of the problems the string is inextensible. What does that mean? Again, I will take the help of the same system that we have been dealing with for the last 2 points, or last 2 assumptions. The same system, the pulley mass system. Let's say again M2 is greater than M1, and I leave the system as such, then this whole thing starts coming down. M2 comes down and M1 goes up. And in most of the scenario, we see that, if M2 is coming down with an acceleration of little a, then M1 is going upward with an acceleration of little a. See, this is only possible if your string, as shown like this blue little string, if the string is inextensible, then this formula is valid. Otherwise, this is wrong, because there is some amount of tension acting in the spring. So that can cause an extension in the spring, and the string will be no longer a rigid body. It will have deformations within the string will have deformation within, and whatever displacement you get here won't be equal to the displacement that the string, or in turn the mass, will have at this particular point. To make it a little bit more clear, let's say I'm taking a small portion of that thread and I'm applying a force capital P. The thread is having an area of cross section capital A and a Young's modulus E. Then if I apply a load of capital P, then I will get a deflection given like this. This is simple Hooke's law, no magic. This is simple Hooke's law. So by the assumption of inextensible string, we are saying that my string is having a very high value of Young's modulus and area of cross section. So for small values of tension or for reasonably high values of tension in the string, my string is going to behave as a rigid body. It is not going to extend. Given that, then you can say whatever displacement the thread will feel here, the same will be felt at a point here. The same will be felt at this point also. There is no relative deformation if the string is inextensible. So that that tells you that if m1 comes down with an acceleration of little a, sorry, if m2 comes down with an acceleration of little a, then m1 should go upwards with an acceleration of little a. There are other ways of proving this, but for the time being this is good enough. I would like to prove the same in a much more formal way. Let's say I have defined two coordinates, little x1 and little x2, like this, which will tell you the position of the masses, which will tell me the position of the discrete masses m1 and m2. Now if I go ahead and say that my string is inextensible, that effectively means the length of the thread won't change. The length of the thread, which is a constant, which it can be written like this, little x1 plus capital SC, as shown over here, the portion which wraps over the pulley, plus what else? x2. Now I can take the time derivative of this. Since c is a constant, I will end up with 0. Then x1 dot, which is simply the velocity of the mass m1, plus again sc is a constant, so I take the time derivative of that particular portion, again I will get 0, plus x2 dot, which will be the velocity of the discrete mass m2. Now I can again go ahead and differentiate it once more. That will give me x1 double dot is equal to x2 double minus x2 double dot. This, we are talking about accelerations here, and we are talking about taking the derivative with respect to time. So this clearly tells me, this expression clearly tells me in magnitude the acceleration of both particles are the same. But when m2 is going downwards, my m1 will move upward. That's what the minus symbol or the minus sign over here tells me. So this is a more formal way of telling that when you have an inextensible string, the masses that you are connected, that you have connected across to the ends, will have the same acceleration. The next assumption that I want to talk about is this: no slipping between pulley and rope. What does that mean? See, if you want to have this kind of a scenario, then there should be friction between the pulley and the rope. Then only the no slip condition will occur. Same as that of a cylinder rolling over an inclined plane. There also, if you want to have no slipping between the cylinder, or if you want to have a no slip condition at this particular point, then you need to have friction between this surface and the cylinder surface. Okay, so what does this mean? This means that since there is friction, the pulley will be rotating. Let's say the pulley is rotating with an angular velocity of, let's say, call little omega. And if capital R is the radius of the pulley, then at the periphery of the pulley, the points will be having a velocity of, they will be having a velocity given by v equal to omega times r. I'm only speaking in terms of magnitude. I'm not going into the vector representation of things. So this is the velocity of a point on pulley. I will call it VPP. Similarly, there will be a linear velocity for the rope as well. Let me call that VR. Because in this scenario, M2 is greater than M1, so my whole system is coming down. So the rope is moving, so it has got some velocity at all these points. If you assume that there is no slipping between pulley and rope, then that essentially means velocity of the rope is equal to the velocity of the pulley at the periphery. So that will be simply VR equal to omega R. No slip boundary condition is not something which is dedicated to mechanics. We will see this in fluid mechanics also. We will see this when we talk about belt drives also. In fluid mechanics, when you say you have a fixed plate and when there is fluid flowing around the plate, then you will say at the boundary, at this particular boundary, the fluid velocity will be zero. This comes from a no slip boundary condition. Clear? So this is what no slip boundary condition means for a pulley and rope system. That essentially means this will act as a tool for us to connect the two motions, to connect the rotation of the pulley with the linear motion of these two discrete masses. This is fairly useful in helping us to reduce the number of degrees of freedom for a particular problem. Before I wind this video, one last assumption I need to talk about: massless pulley. See, if I draw the free body diagram of the pulley like this, let's say this is acting T1 and this is acting, this tension is T2. So what kind of motion is my pulley undergoing? If there is friction, then it is rotating. It is undergoing a simple pure rotation motion about this point, this pivot point. Then I can write the equation of motion like this: J theta double dot is the angular acceleration, which is d omega by dt, where omega is the angular velocity, is equal to, if I take this as the positive direction, then T2 times capital R, let's say capital R is the radius of the pulley, minus T1 times capital R, because this force is resisting the motion, but this force, T2 force, is actually helping the motion along the positive direction of theta. This is the positive direction of theta, in case you have missed out. I've taken the clockwise direction as the positive direction of theta. Doesn't matter. If the pulley is massless, what does that mean? That means my J is 0. Why? Because my polar moment of inertia J is defined as integral r squared dm, where integration runs throughout the body. So if the pulley is massless, that means my T2 equal to T1. So we have looked at 5 assumptions which are listed one after the other here. So we looked at what is the meaning of saying that your pulley is frictionless. That means your pulley won't move. Your rope will move, but your pulley won't move. Then what is the implication of telling that I have a massless rope? That means the tension is uniform across the string or across the cord until it sees the next disturbance or the next mass or the next pulley in a mass and pulley system. Then implication of massless pulley, the last one to see, it tells you that both sides the tension has to be the same, because I don't have a J, polar mass moment of inertia. Then the very important inextensible string assumption, which clearly tells us that when you have two masses connected through an inextensible string, then whatever be the displacements felt by the mass m1, that will be transferred to the mass m2 also. And we have arrived, or we have proved the same in a formal fashion as well. And then we looked at what is the meaning of saying that there is no slip between pulley and rope, which will effectively help us to connect the two motions, the pure rotation of the pulley about the pivot point can be related to the linear translation or the linear motion of the discrete masses using this assumption. I hope this video was useful, and next time whenever you hear these words, appreciate what it really means. And in case if you see some other new assumptions, please tell me in the comment section, so I will make a video on that as well. Thanks for watching.